Hi everyone. One of the most fundamental objects in calculus is this idea of a limit. It's going to help us define things like the derivative, integration, which is going to be next term. When we get to sequences and series, we're going to be looking at limits in those contexts as well. The limit turns out to be everywhere in calculus. And this is the main topic that we want to introduce right now. What do we mean by a limit of a function? So let's look at an example. We have a function here, f of x equals x squared minus x minus 2 all over x minus 2. What is the domain of this function? So when we're given a function in terms of a formula, in terms of this expression, we can assume that the domain is just the largest set of x values, set of real numbers for x, that we can plug into the function and have it still make sense. So are there any values of x which we can't plug into this function? Well, the issue seems to arise in the denominator. I have this x minus 2 there. What happens if we plug a value of x in where the denominator is 0? Well, then we'll be trying to divide by 0, which we can't do. So there's an issue there. We can't plug a value of x in for which the denominator turns out to be 0. So we have to exclude x equals 2 from the domain. Any other x values we have to exclude? Well, any other x value, we work out the top, that's just some polynomial, that'll be some number. The bottom will be some number, non-zero number because we're excluding the case when x is 2. And one number divided by a non-zero number. We can work that out. So it makes sense to plug any other value of x in to this function. We can certainly work out the values. So the domain of our function f in this case, well, it would be the set of all real numbers excluding 2. So we can write that using set builder notation as x, and this little symbol here kind of looks like a backwards E. It means element of, or you can, in short, just read it as in. So let me rewrite it so it's a little bit more clear. Looks like that. So the set of all x in the set of real numbers are such that, this colon we read as such that, sometimes people use a vertical bar instead, such that what? What are the conditions we want to have x satisfy? Well, we want it to be any real number except for 2. So we need to say, well, such that x is not 2. And that builds up the set, which represents the domain. This is using set builder notation. We could also use interval notation, which might be more familiar to you. In this case, we want to build up a set excluding 2, so we can include everything from negative infinity to 2, not including 2, so we've got the round bracket there, union, everything from 2 to infinity. Again, the round brackets indicate that we're not including those values, so we're not including 2 in this case. If we had a square bracket there, it would mean the interval including the endpoint 2. And also, infinity, negative infinity, those aren't numbers, those are just concepts representing the idea that things go on forever, so we always use the open bracket notation around those. Okay, so there's our domain. What does this mean? Well, it means we can't plug 2 into the function. But what if we want to know what the function is doing around 2? Is it behaving in some way? Can I sort of say, well, as x gets close to 2, what's the function doing? I can't say exactly what happens at 2 because I plug 2 into the function and, well, it's not defined. What's going on around 2? What are the function values around the x values of 2? Well, we can work out a table of values for this. Let's plug in x equals 1, for example. So there I would just work this out. F of x is, f of 1 is, well, be 1 squared minus 1 minus 2 all over 1 minus 2. So the numerator would be negative 2 and the denominator would be negative 1. So this works out to be 2. So we fill that in our table. And we can just do this for all the other values as well. We'll see a quicker way to fill this table out in a second. Now, what do we observe? Well, as these x values get closer and closer and closer to 2, in this case we're approaching 2 from values slightly smaller than 2, or to the left if we're thinking about the number line as being horizontal, we're approaching 2 from the left side, 1, 1.9, 1.99. What is the value of our function doing? Well, these seem to be heading towards which number? Right, 3. They seem to be going towards 3. Similarly, if our x values head towards 2 from the right, so a little bit above 2, we're creeping closer and closer to 2 from the right-hand side of 2, then the function values are getting closer and closer to, well, 3 again. So it looks like f gets close to 3 if we take our x values closer and closer to 2. In fact, for x values not equal to 2, we can rewrite the expression for f as follows. Notice that we canceled off the x minus 2 from top and bottom in order to simplify it down to x plus 1. Now we can only do this when x is not equal to 2. When x is equal to 2, this would effectively be 0 over 0, so we wouldn't have that expression making sense in the first place. But when x is not equal to 2, we can certainly cancel x minus 2 from top and bottom, because those would be non-zero numbers. In which case, f can be rewritten as x plus 1. So the values of the function f for an input x are exactly the same as just taking x plus 1, adding 1 to the input, with the exception that we're not allowed to plug 2 in. So what does that mean? Well, it means we can easily sketch the graph of this function f. What looked to be maybe complicated at first, some sort of rational function, turns out to be, well, it's just, f is just a linear function, x plus 1. So it looks something like this, with the exception that it's not defined at 2. So at 2, there's a hole. And so this is our graph of y equals f of x. It passes through -1 there. Of course, it passes through 1 here, because this is really just the line y equals x plus 1, but it's got a hole in it. Now, the question about what is the function doing around x equals 2 now becomes very apparent, because when x is around 2, our function value is hovering around the height of this hole. What's the height of the hole? Well, I can figure out what the height of that hole is by just realizing that, well, the equation of the line where the hole is filled in is y equals x plus 1. So the height of that hole must be 2 plus 1, or 3. So that tells me then that as x gets close to 2, my function values of f are close to 3, which is what we observed using this table of values, but here we used a little bit of algebra to figure that out as well. So in either case, what we have is, as x gets closer and closer to 2 from either side, the function values are getting closer and closer to 3. So we call 3 the limit of f of x as x approaches 2, and we use this LIM notation, this limit notation, to summarize this statement. So we got this sort of intuitive idea of what a limit is. It's sort of what the function's doing around the point you're interested at. Let's give it a more precise definition. So we write LIM underneath it, x arrow a of f of x equals L, and we read it as the limit of f of x as x approaches a is equal to L, precisely when we can make the values of f arbitrarily close to L as we like, by taking x sufficiently close to a from either side, but not necessarily equal to a. So what does that mean? It means that we're trying to get our function value close to this L value by taking our input values, our x values, close to a. So this is supposed to capture the idea of what is the function doing around a. So let's see how we can apply this in practice. Let's guess the value of the limit as x goes to 0 of sine of x over x. Now right now, all we can do is say, well, we're trying to find this value L, so that f of x is arbitrarily close to L, provided that x is close to, well, in this case, 0. So let's just work out a table of values and see what we can find. Here I'll put my inputs, x, and here I'll put my outputs, sine of x over x. And we want values of x that are getting closer and closer to 0. Notice I can't actually just plug 0 in to the function, because I would get sine of 0 divided by 0. Can't divide by 0. So there's an issue here. The sine of x over x doesn't have 0 in its domain, but we're still trying to answer the question, what is the function doing around 0? What's its behavior there? Well, let's just work out a bunch of values. We can do, x equals 1, and then creep a little bit closer, x equals 0.1, maybe a little bit closer, 0.01, and let's just try to creep up on 0 and see what our function values are doing. So we'll take these numbers heading towards 0. And if we recall that, well, these things have to be done in radians, because in calculus we always use radian measure for an angle. So when we pop these values in, sine of x over x, you can use a computer, a calculator, whatever you like, we can fill in this table of values. And so what do these numbers seem to be approaching? As these x values go towards 0, what do these function values seem to be heading towards? We're getting more and more 9s along. So these things seem to be heading towards 1. So then we'd say that the limit as x goes to 0 of sine of x over x is 1. And that's just what we get from these table of values. So a rough sketch of what this function sine of x over x looks like. It sort of looks like this. And right up here, 0 is not in the domain, so it's got a hole, and then it comes back down and it sort of oscillates away. And it gets smaller and smaller as it goes, just because we're dividing by, sine of x is always trapped between -1 and 1. We're dividing by, well, as x gets bigger, dividing by a bigger number, so this should shrink down to 0. So it should get closer and closer to 0. But the key feature here is that there's a hole in the graph. And we found that the height of that hole should be 1. What's the function doing around x equals 0? The function's sort of hovering around 1. It seems to be sticking close to 1. That's what this idea of a limit is trying to capture. We don't know the value of sine of x over x at x equals 0 because it's undefined there. But we can ask the question of what the function's doing around that point. This is this notion of a limit. Now we will come back later on and see that, well, oftentimes tables of values can be misleading to get limits, so we need some more algebraic ways to come up with these values of these limits. And we will revisit sine of x over x and show definitively that the limit is 1 in this case, and we'll use a little bit of trigonometry and algebra to get that. Okay, what about this next example? What can we say about the limit as x goes to 0 of absolute value of x over x? Well, one thing to note is absolute value of x is really defined to be a piecewise function. If x is positive, then the absolute value does nothing to it. Just x comes out. But if x is negative, then the absolute value essentially strips that negative sign away. So what it actually does return is just negative of x. Because if x is negative to begin with, then negative of x should be a positive number. So we can rewrite this function absolute value of x over x as follows. Absolute value of x over x is defined to be 1 if x is bigger than or equal to 0, or negative 1 if x is less than 0. And so we can sketch a graph of it. What it's doing is it's 1 for positive values. Oh, I need to be careful here. Notice that I kept the equal sign when I shouldn't have. As soon as I divided by 0, I lose x equals 0 from my domain. So this needs to change to strictly greater than. 0 is no longer in the domain once I throw this dividing by x in the expression. And it's a negative 1 when x is negative. So what's going on around 0? Well, as x goes to 0, is absolute value of x over x approaching some particular number? Is it approaching some value? Well, no. Because if I approach 0 from the right-hand side, my function is heading towards 1. Well, it's actually 1 always, but so it's heading towards 1. But if I'm approaching 0 from the left-hand side, my function values are always negative 1. So the limiting value would be negative 1. And so they're not matching up. There's no one number that the function value gets close to as x gets close to 0. It gets close to two different numbers depending on which side you're approaching 0 from. So in this case, we would say that the limit does not exist. There is no value L such that the function gets close to as x gets close to a from either side. And so that's the key. Back here in our definition, the function has to get close to L as x gets close to a from either side of a. And in this case, it doesn't get close to a single L value. But of course, you'd like to say, well, okay, it doesn't exist, but it really doesn't exist for a particular reason. It's doing one thing on one side of 0, and it's doing something else on the other side of 0. So this is where we have this idea of right and left-hand limits. So we write LIM as x goes to a with a little plus sign as a superscript or exponent. So let's just indicate here if it's hard to see. This is a plus sign in the exponent. And that just means you're coming to a from the positive side of a, or just a little bit beyond a, or from the right of a, if you want to think of it that way. We're thinking sort of a number line here, and a is on the number line. And we're coming at a from things that are a little bit bigger than a, which is why we're using the plus there. So the limit as x goes to a from the right of f of x is equal to L if we can make the function values close to L as we like by taking x sufficiently close to a, but only from the right of a. We don't care what's going on to the left of a, just from the right of a. There's a similar notion for a left-hand limit, and there you would use a negative sign in as a superscript, or if you want to think of it as an exponent. We typically call those superscripts because they're not algebraic things. They're just a notational convention. Let's revisit the previous example. The limit as x goes to 0 from the right of absolute value of x over x. Well, in this case, as we head towards 0 from the right, our function values are close to 1. So this limit should be 1. And the limit as x goes to 0 from the left of absolute value of x over x, well, that would be negative 1. Because as we head towards 0 from the left, our function values are close to negative 1. Now, this idea of a left and right-hand limit is to just go one step further. We found that in this previous example that the limit doesn't exist. Okay, rather than just saying it doesn't exist and being done with it, well, there's some reasons why it doesn't exist. It doesn't exist because it's doing something on one side of 0 and something else on the other side of 0. So this idea of a left and right-hand limit are just to focus our attention on what's going on one side versus what's going on the other side. So we could say the limit doesn't exist. The reason this one doesn't exist is because it's approaching 1 on the right-hand side of 0, but the function's approaching negative 1 on the left-hand side of 0. So let's have a look at another example. In this case, we've got a piecewise defined function. It's got 5 different pieces here, depending on where you are on the x-axis. So let's sketch our coordinate system. What does our function look like? Well, sort of the breakpoints are negative 1, 0, and 1. So let's jot these down. There's negative 1, there's 0, there's 1. And what's going on? Well, when x is negative 1 or below, so to the left of negative 1, it looks like x plus 1. So it's a linear function of slope 1 shifted up by 1 unit. So we can plug negative 1 in to see where the point is on here. Negative 1 plus 1 is 0. So it actually passes through this point. And it looks like this. So maybe I'll just move this number over since I'm going to write over top of it. So there's negative 1. Now, from negative 1 to 0 on this interval, the function looks like x squared. So it's part of a parabola. But notice that at negative 1, there's an open bracket here. So x squared, that piece of the function is not defined at negative 1. So there's an open point there. Then it looks like a parabola. At 0, notice at 0, the value is 1. So I got a hole there again. But it actually takes the value of 1 there. So there's our filled-in point. So at x equals 0, the function value is 1. And then you continue on with the parabola, x squared from 0 to 1. And notice it's a square bracket, so 1's included. And then from this point forward, it looks like an x plus 1 curve. So it's a linear curve again, starting at x equals 1 and moving on, but not including x equals 1. So to figure out where it starts, I can just say, well, when x is equal to 1, this is 1 plus 1 is 2, so there's a open point there, and then it looks like a straight line again. So this was height 1, that was height 2. And so there's what our function looks like. It's a mix of linear things, points, and quadratics. Let's answer some questions about the limits now. What is the limit as x goes to -1 from the left? Notice a little negative sign as a superscript, so this is saying we want to know the left-hand limit of f of x. So as we head towards -1 from the left, we only care about what's going on to the left of -1. I don't care at all what's going on to the right of it. So as I head towards -1 from the left, my function values are getting closer and closer to 0. As I head towards -1 from the left, my function values are getting close to 0. As I head towards -1 from the right, from this side, my function values are heading towards the height of that open hole there. And so that's 1. So my function values are heading towards 1. Key things to keep in mind: when you're looking at a limit, you don't care what's going on at the point. When you're looking at the left or right-hand limits, you don't care what's going on the other side of the point. So here we only care about what's going on to the right of -1, not what's going on at -1 or to the left. So as I head towards -1 from the right, my function values are caught on this part of the parabola, heading up towards 1. What about as I head towards 0 from the left? As I head towards 0 from the left, my function values are heading down towards 0. So what's going on around 0? The function's getting close to 0. Notice I don't care what's going on at 0. At 0, the function's a completely different value. It's 1. But the limit is 0 because that's where the function values are heading towards. I don't care what's going on at the point, just what's going on near the point. What's going on as x goes to 0 from the right? Still, I'm heading towards 0. And lastly, as I head towards 0 from either side, notice there's an absence of a plus or a minus in the exponent. So I'm looking at the general limit now. Either side of 0, what's going on? Well, no matter what side I approach 0 from, my function values are heading towards 0. So this last little bit summarizes the connection between the general limit and one of these one-sided limits. So if the general limit as x goes to a of f of x is L, then that means both of the one-sided limits have to go to L as well. And conversely, if both one-sided limits, if I head towards a from the left or head towards a from the right, and they both go to L, whatever they do, they both go to the same place, then the general limit is also L as well. So we can detect whether a limit doesn't exist by maybe showing that the left and right-hand limits are different, kind of like that absolute value x over x example that we did on the previous page. Okay, so that's the connection between right and left-handed limits and the general limit. Let's sketch the graph of this function. F of x equals 1 over x plus 1 squared. Now we're just sketching, so that we're just trying to get a, sort of a rough idea of what the graph looks like. So here, we just notice that, well, there's a problem at a particular x value, namely the x value that makes the denominator 0, because then we'd be dividing by 0. So at -1, there's an issue there. The function's not defined there. So I'm just going to put a dotted line indicating that, well, the function's not defined there, so it's not going to touch this dotted line. What's going on around the dotted line? Well, as I get closer and closer to -1, what's happening? We're getting closer and closer to -1. X plus 1 is getting closer and closer to 0. So as x gets close to -1, x plus 1 gets close to 0. And in particular, x plus 1 squared gets close to 0. But that means then 1 over x plus 1 all squared gets close to what? Or is doing what? As x plus 1 squared gets close to 0, the reciprocal of it must be getting big. So this must be heading off to infinity. The reciprocal of a small number is a big number. So these seem to be blowing up. So we're heading off in this direction from either side. Now what about as x gets really big? As x gets really big, x plus 1 is really big, squaring it's really big, 1 over a really big number is a really small number. So these things seem to be getting small as x heads off to infinity. And because there's a square there, I know everything I'm dealing with is positive, so I only have to work above the x-axis. I can get one more bit of information. When x is 0, plugging 0 in, 1 over 1 squared, that's 1, so I know it passes through that point there of height 1. So there's a rough sketch of the graph. Now, we can characterize what's going on around -1 in terms of a limit as well. We can say that if a function is defined on both sides of a except possibly at a itself, then we write the limit as x goes to a of f of x is equal to infinity to mean that the values of f can be made arbitrarily large, as large as we please, by taking x sufficiently close to a. Now in this case, we'd say that the limit as x goes to -1 of 1 over x plus 1 squared is infinity, since regardless of which direction I approach -1 from, the function values are blowing up, heading off to infinity. So we say blowing up in this case usually. Okay. So I want to just be very clear on something here. I'm not saying that the limit exists at -1. In no way am I saying the limit exists. In fact, the limit does not exist at -1. But it doesn't exist in a very precise way. Okay, so you may be thinking right now, well, you just wrote the limit is infinity. How are you saying that the limit doesn't exist? Well, remember, the definition of the limit is the limit of a function is a value, a real number, such that the function gets close to that real number as x gets close to a. This function is not getting close to a real number. It's increasing indefinitely. So it's not getting close to a particular L value. It's just blowing up. So the way we summarize this is we say, okay, we could say the limit doesn't exist, but I want to be more precise. The limit doesn't exist because the function's blowing up. So we adopt this sort of shorthand convention for the full statement that the limit doesn't exist because the function's tending to infinity as x goes to infinity. We say instead that the limit as x goes to a of f of x is infinite. The distinction is that infinity is not a number. Infinity is a concept, really meaning that things go on forever. So I'm not writing a statement here where I've got a real number on the right-hand side. I've got a statement here where I've got sort of a concept on the right-hand side. So the limit doesn't exist, but this is characterizing why it doesn't exist, because the limit's infinite. The function's blowing up. Okay, this is a subtle point, but it does come back a few times to sort of haunt us if we're asking questions about existence of limits and then limits that tend to infinity. So let's look at another example. We want to sketch the graph of this function. I'm going to just rewrite it first of all, massage it a little bit, maybe make it look a little bit more inviting to deal with. In this case, I'm just going to write the 3 as 4 minus 1. And I'm going to do that because now I can divide the x minus 1 into that piece of the numerator. Okay, at this stage, now I want to figure out how to sketch this. Well, there's a problem at 1. It's not in the domain. So I'll just draw a little dotted line there to indicate that I know the function can't cross that line because 1's not in the domain. What else can I do? Well, I can look at what's going on around 1. So I'm going to look at what is the limit as x goes to 1 from the right of 1 plus 4 over x minus 1. Well, what's happening here? As x goes to 1 from the right, so we're slightly bigger than 1. X minus 1, well, that's going to be positive because x is slightly bigger than 1, but it's a small positive because x is getting close to 1, so x minus 1 is getting close to 0. So this thing is getting close to 0, but through positive values. So I'll just write that as 0 plus. That means that the ratio 4 over a small positive is a really big positive. So this is heading towards positive infinity. The ratio is. So as the denominator gets to be small in positives, the reciprocal, or 4 over a small positive, is a really big positive. And so this thing is blowing up to infinity. And so adding 1 to it, that's still getting big. So this is heading off to infinity. So again, just to summarize, the limit doesn't exist. Doesn't exist in a particular way. The function's blowing up. It's blowing up to infinity there. So we use just this shorthand notation to describe the limit doesn't exist, but it's because the function's blowing up. And so that's what we're using here to describe that. What's going on as we head towards 1 from the, in this case, it should be from the left. Okay, as you head towards 1 from the left, x slightly smaller than 1. A number slightly smaller than 1 minus 1 is going to be close to 0, but negative. So this is getting close to 0 through negative values. So it's a small negative. Taking the reciprocal of that is becoming a big negative. Adding 1 to it, still a big negative. So this is heading off to negative infinity. So our function is doing this around around 1. And we can also say a little bit more. As x gets really big, x minus 1 gets really big, 4 over really big is really small. So this thing is getting close to 1 plus a small number. So it shouldn't dip below this line of 1, but it should get close to it. It should be getting closer and closer and closer to it. And similarly for the other side. We should be getting closer and closer and closer to it. Now exactly where does it cross these axes? Well, you could figure that out. When x is 0, g of 0 is 3 over negative 1 or negative 3, so I know it's going through negative 3 there. And when is the function value 0? Well, if I plug x equals negative 3 in, I get 0 over negative 4, so that would be 0. So it also passes through that point, which has an x value of negative 3. So you can fill in these details, but we get the rough idea of this sketch. And most of it was coming from this idea of just saying, okay, what's going on when x gets close to this? What's going on when x blows up to infinity? And those are the kinds of information that we were using to sketch this graph. As another example, you can look at example 10 in the text, where they discuss the tangent function there. The tangent function has this property that there's a whole bunch of these vertical lines where the function seems to be blowing up at. These vertical lines are known as asymptotes, so the tangent function has infinitely many of these asymptotes, and that's what this example is getting you to look at in the text. And here's the formal definition of an asymptote. The line of x equals a, so this vertical line x equals a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements is true. Either the general limit as x goes to a of x is infinite, or one of the two handed limits is, either the left-hand limit or the right-hand limit is. Or the function has a limit of negative infinity, or one of the limits does. So in some sense, these are just trying to capture all of the cases. We've got this line, x equals a. That's an asymptote if the function does that, or that, or that, or that. If it's blowing up either to positive infinity or negative infinity as you approach it from one of two sides, possibly both. So that's what these cases are all referring to, is that you're either approaching from the left or the right, or both sides, and you're blowing up or blowing down to infinity. Okay, so I want to leave you with a question about vertical asymptotes. You'll notice at no point did I say a vertical asymptote is defined to be a line for which the function gets close to but does not touch. And I've been deliberate not to say that up until now, where I'm trying to point it out. I've been deliberate not to say that because it's something that people do say, but it's not true. It's not true. A vertical asymptote, by definition, is a line, x equals a, for which one of these limits holds. The limit is either positive or negative infinity as you approach from one or both sides. It hasn't said anything about touching the vertical asymptote. The function, could it touch the vertical asymptote? Could it not? I'll leave you to think about that. Maybe try to think of an example where you have a function that has a vertical asymptote and the function also touches that vertical asymptote. We'll pick that up in class and maybe we'll discuss it a little bit more. Anyways, that's it for this lecture, and we'll see you next time. Thanks for watching.